My name is Tyler Bro, and this is Physics 2212 Lab 5, Magnetic Braking. We're going to start with introductions and concepts, then go into assumptions and models. We will then go over the experimental procedure and compare this with a computational model, and lastly, we will go over the discussion. The purpose of this lab is to collect observational data of a magnet falling through a tube of aluminum foil. We will then model this phenomenon in GlowScript, and lastly, compare the expected and observed values. A preview of the results: the average time to fall was 1.15 seconds, and the predicted time was 1.129 seconds. Some key concepts. First of all, Faraday's law relates induced electric field to magnetic flux via the following. The surface integral of E vector dot dl vector is equivalent to the negative change in magnetic flux over time, with this change in magnetic flux over time being defined with the following equation here. And this electric field induced by the change in magnetic flux is in the same direction as the induced current. Magnetic force is defined by F equals I L cross B, and when considering a loop, this simplifies down to I times 2 pi r times B times the sine of theta. Newton's third law is also very important here. It's every force has an equal and opposite reaction. That is to say, the magnitude of magnetic force on the loop is equal in magnitude to the magnetic force on the magnet and opposite in direction. Another important concept is Ohm's law. V equals IR, which is also equal to EMF, which is also equal to the negative change in flux over time. So here you can see a visual representation of induced current via change in a B field. Our system is the falling magnet, and the surroundings are the foil tube and also everything else on Earth. Some assumptions made are that only forces on the magnet are gravity and the force from the loop, and that the magnet falls always with the north pole facing exactly down. So the experiment. Relatively simple. The north pole of the magnet was marked and key dimensions were taken, such as the mass of the magnet and the width of the foil, the tube radius, and its length. The magnet was then dropped through the tube 5 times with the north pole facing down, with the time to fall through the tube recorded each time. The average was then computed, which was eventually compared with the expected value of the computational model. Results of this: the average time to fall was 1.15 seconds. Length of the tube was 0.4 meters. Width of the foil was 0.005 meters. The inner radius of the tube was 0.0125 meters. Adding the width and inner radius gives you the total radius, 0.013 meters. The magnetic dipole was taken from what we calculated in Lab 3, which is 5.365. And the mass of the magnet was 0.044 kilograms. Now the computational model. You can see here it's a little small, but I will try to read as best I can. First, some physical constants were defined, and the graph was initialized. Then we had to create the geometry of the aluminum foil in GlowScript, so all the measurements taken were input here. Next, some numerical parameters of the simulations were defined. Then we created the tube of aluminum foil as a series of rings stacked along the y-axis. With this created, we now create the bar magnet. We put in the properties, and then we actually visualize it here. On the next slide, we then define initial conditions with the magnet having a velocity of 0 at time equals 0. We now create a function to calculate the magnetic field, which was pulled from my code from Lab 3. And we create a function to calculate magnetic flux using the equations previously discussed. And now the simulation loop is defined here. And this is just more of that. And at the end of the loop, you can see the magnet's velocity and position are updated at the end, and then it is repeated until the magnet is out of the tube. And this is all plotted on a curve. You can see here are the results. On the left, you can see the little model. This magnet, falls downward through the tube. And on the right, we have the graph that ends up being plotted, velocity over time. And you can see the result of 1.129 seconds. So our estimation was very close. It's possible that the magnetic moment from Lab 3 was incorrect, which would explain the slight difference in time. And some possible sources of error are precision in recording the time to fall, contact between the magnet and tube, air resistance, and inaccurate measurements of dimensions of the tube. So what if the resistivity of the conductor were reduced to near zero? Near zero resistivity would equal near zero resistance. This would lead to a very large induced current via Ohm's law, since current and resistance are inverse, which would in turn result in a very large magnetic force on the loop. By Newton's third law, this means the magnet would also feel a greater force and thus would fall slower, as this force would be much closer to gravity. What if holes were cut in the tube? Holes would disrupt the continuation of the rings in the aluminum that were used in the simulation to define the tube. This would reduce the overall induced current, and by the logic in the prior slide, would ultimately make the magnet fall faster through the tube. Thank you.